In this short video, I'm going to talk about torque. And torque is to rotation what force is to translation. So any equation that you learned and you know something about translation and force, switch it over to rotation and torque. And so I'm going to talk about how to calculate it. So we're talking about the first case, a general case, and normally you're going to do torque around one of two places. Either you're going to have some sort of axis, some center of rotation, or you're going to have a center of mass. And you're almost always going to calculate torque either about the center of rotation, if there is one. If there is no fixed center of rotation, then you're going to do it about the center of mass. So this case is case one, we have an axis in here. And so it's also very important for torque is when you draw your feedback diagram or think about it, is to put exactly where the force is acting. So if you have something rolling down the slope and there's a part right here and there's a normal force here, you want to draw that normal force exactly where it is in the free body diagram. And if there's a friction or something, you don't want to put it in the center. You want to put it exactly where it acts. If it acts right at that interface between the ground and the object, you put it there. If there's a rope that's pulling here, you don't draw the force of the rope here, you draw the force of the rope exactly where that rope's acting. Okay, so it's very important to always draw in your free body diagram exactly where that force is acting on your system that you chose. Okay, so we're going to say this force is somehow acting exactly at that point on the system, and here's exactly the center of rotation, and here's the force, direction, and magnitude. Okay, so now to calculate torque, we're going to draw a line from the center of rotation to the exact point where that force is acting. And that line, and that vector we'll call R. So from the point of rotation, if there is no point of rotation, then it's the point from the center of mass. From the center of the mass to the exact point where that force is acting. That's my R. Now torque is a vector, and it's just the cross product of R cross the force. And so the magnitude of that is the magnitude of R times the magnitude of F times the sine of the theta. And theta is whatever angle there is between the R. So take your R vector, your force vector, draw your theta, whatever that theta is, that's what you're going to use here. Okay? And then so like for case number 2 here, I drew exactly, I'm again rotating about a center rotation. There's exactly where my force is acting. It's acting this direction. And in this one I've shown that from the center rotation to that point where it's acting is perpendicular to the force. So in this case the sine of theta, the sine of 90 is 1, so it becomes just the magnitude of these. In case number 3, I put exactly where that force is acting in the exact direction it is. I draw from the point of rotation to that point of the force. Here you can see that theta is 0, or you can say 180. Either case is the same because the sine of 0, sine of 180 is the same. And so we get so this has no torque. And yeah, then if there is no fixed axis, you pick the center of mass. So put exactly where that force is acting. The exact force direction, both direction and position are very important. Draw the point, the R, from the center of rotation to where that force is acting, and then you do the same equation. Now it's a vector, so here is I'm going to pick the Cartesian coordinates. So we have X, Y, and Z is going to be out of the board, and you can't really see it. So you can't. So I kind of drew it this way. So cross product is. So you start, so if R is this way, for this example, R is this way from let's say the center of rotation was here, and R is this way, and the force happened to be this way. In this case, there was my FR. Right, so R cross F. So you start with R, you go to F, and you see that the direction is of this vector is out of the board. So that director, if the plane that has the R and the F in it, the the torque is going to be perpendicular to that plane. So in here, I cross K is J. In this case, we're going to start with the R, go to the F, and that goes inward to the board. So we'll see. So this one is going to be a minus K. It's going to make it turn this direction. Okay. So what we're going to use for torque, net torque a lot with is we're going to for change in angular momentum about the center of rotation. It's either an axis or center rotation, could be the center moment, is the net torque around the center rotation, which we're going to calculate figuring out R and F, however it is, times that vectorially times delta T. So that's where we're going to often use it. So just remember, put the force exactly where it is, where it's acting, and then draw R from the center of rotation, whatever that is, to that exact point, and define theta that way.